Okay, good evening everyone. We're gonna start the lecture now. So if you want to follow the lecture on Z-Things, this is the link. Let's get going. Oops. So today we're gonna start talking about Apache Spark. So we spent the last 3 weeks, we dived in Hadoop, how we handle Hadoop, how we create MapReduce jobs, how we configure Hadoop, how we make sure that we maintain some level of security on Hadoop. So now we're gonna go to Spark, and you'll find we'll discuss some differences, the motivation of Spark and why it was created, and what's the difference between Hadoop and Spark. So, and regarding to Spark, like definitely whoever thinks big data and big data processing, or in terms of how to maintain cluster computing within big data analysis, that Hadoop come to mind as the go-to solution. So why would we want Spark? So we might think, okay, MapReduce is already doing a good job on that term, that it's going to take, segregate these small tasks into key, take the data and convert them to key value pairs, and then segregate these key value pairs into nodes in the cluster, and then do the mapping, the reducing, and hence it can maintain some level of parallel computing, hence speed. So why would we want to go to something like Spark? But like for MapReduce, it's more, as I mentioned now, it's more into, okay, you're taking this huge chunk of data and you're trying to process it on this unreliable cluster, and it's more like a bad job. It's a one-pass job that you push the data to the cluster and then you get results. But people were, data scientists were happy with that, but at some point they needed more. So there are it's now more than one pass. So it requires to be more iterative, more multiple passes of data. So it's not like one batch, you throw the data and then you get the results. There was a need for multi-pass, complex calculations, more interactive. So as you have seen with MapReduce, so you submit the job and then you get the results. So there is less interactivity. There are some tools to sit on top of Hadoop and MapReduce that can allow you to do querying, like Hive or Peg. So it can allow you this level, but at the same time, it's not as fast as you want it to be, because you're still going to wait for the results of the job, the MapReduce job, then you can get results. So it's less interactive. And when we're talking real-time processing, so if you have fast data, so if you have logs that keep coming and accumulating every second, then when you're thinking MapReduce and then a batch job, that might not cater your needs, because then say, okay, what can I do with all this data coming to me? I cannot wait till the first batch is done, then I submit a second batch, and so forth. So there is a need for more stream processing. So although there are some special use cases, like specialized tools that sit on top of MapReduce that can, on some level, provide that, there is for graph processing, there is this Spriggle. So it's allowed that MapReduce in general do not process graphs, but they have some more abstraction on top to allow that. Storm is another tool that's part of the Hadoop ecosystem that allow you also to do stream processing, but on some level that is less interactive, and the speed is less what you expect it to be, and hence becomes the need for Spark. So for you, as you've noticed in the assignment, and even in the table join activity in week 3, in week 4. So for you, what did you notice that MapReduce is not doing properly or is a bit tedious to do the task on MapReduce? So within these specific use cases that you've been through, so for the table join and for the assignment you're doing now, what did you feel the thing that was like, okay, this might be, there should be a better way to do that? Or we are getting something we are not, I don't know what to do. So there is something like, this is one thing that's like, it's an experience you've been through, but it's clearly that within MapReduce, there should be a way that can handle this instant better. Yep. So it's structure and iterating. Structure, what does structure mean? So in terms of structure is how, like the data is structured, or what? Structure of what? Iterating, like here, make sense for, because there is iterative kind of job submission object type. Yeah, so this is more into the custom type. Creating writables. Yeah, creating writables, this is more of a Hadoop. Like it is also relevant here because we'll find out in terms of Spark how they enriched the library to make things, to make your life as developers much easier. Whoa, we're getting smaller. All of them, different types of writable, custom writable, customized class. Oh, girlfriends, oh my God. Structure, creating writables. Okay, so like the things that's relevant here in terms of, okay, the custom writables. So like the library of how Java is handling Hadoop is part of the problem of how we are actually doing that. So it's a bit of a longsome process. You need a considerable amount of line of code in order to execute a MapReduce job. So that has been solved on some instant for Spark. We'll have a look at that. But the most important thing is that I wanted you to pay attention to is what was mentioned in the beginning, iterating. So for both cases, there is more cascading of jobs. So you have multiple jobs, one feeding the other. So what you have noticed is that the results of the first MapReduce job is providing you with an output file. So there is like the first job, second job, and there is a middle output file. And then you take that output file and then feed it to the second job, and then you're doing some more MapReduce, and then you're getting the final results. So with this, it's like, might be obvious that it is less optimum solution, because like here you're creating as a file and then reading the file again into the second job. And like imagine if you have 10 jobs, then like you're creating 5 files and feeding them one after the other. So, sorry, 9 files. So in that sense, it might not be an optimum solution. So definitely like there might be some sort of way to overcome that, specifically if we're targeting speed, stream processing, and like more lightweight interaction with the data. So like this is like generally the normal way. Like here it's like a normal MapReduce. So there is input, map, reduce, and output. So as a general programming model, so as I mentioned, it's more like suitable for one pass. So I send the file, MapReduce, get the results, voila. So when there is more nesting, there is multiple jobs, it gets to be more complicated. And then for iterative operations, there is no clear way, like you need to build your own iterative flow yourself. So it doesn't do that for you as like the programming model. When it is, we're talking Hadoop specifically, so these data are stored on disk. So if it is HDFS or if it is your, like if you're doing the standalone, it is your own file system. So these are all like the intermediate files are going to be stored on the disk. And like for, as we mentioned, for Hadoop, like the usual thing is like in terms of replication for data is that it is triple replicated. So in order to maintain availability, so most of the time it's triple replicated. So these are the things like it is part of how MapReduce work on Hadoop, but they are going to create some issues with if we're talking about more stream processing or lightweight or like iterative jobs. So like normally this is like when you have iterative jobs, so there is like you have an input, first iteration, you write to HDFS, and then for this is your intermediate file, and then you read from HDFS again, and then your second iteration, and then you write to HDFS, and then you read. So depending on how many iterations, you're going to keep write, read, and so forth. When we're talking about query, so it's more like you're trying to query the data set. Like let's say you're using Hive to query your data on like stored in HDFS. So the query is going to all read from HDFS. So there is going to be an I/O operation reading from HDFS and then providing the results. So by nature, any input-output operation to the disk is slow. So because like you're reading from disk, even if you're using SSDs or whatever, it's still much, much slower than memory. And hence, imagine if you have iterative jobs and you keep reading, writing, then that will affect the speed, how fast you can like execute your jobs on the data. And like hence, it's like MapReduce within Hadoop is lacking the efficient primitive for data sharing. So here, when we're talking iteratives, like iterative operations, multiple jobs, they are not sharing the data properly or like in a fast way. So hence, they are relying on the disk, read, write on the disk, make things much more slower than you would want them to be. So here, like, when you can see, like, for each reading and writing, for each job, there is an I/O, disk I/O operation. And hence, it is going to slow down the whole thing. And definitely, when we're talking queries also, like you're reading from HDFS file, and hence you're slowing the whole thing down. And that's like one of the shortcomings of MapReduce. It's like, okay, when it is a bad job and you want just like in a one go, you submit the file and then you just like the calculations happening and then you get a final report, it's fine. But when we're talking about stream of data or fast analysis, or you want more interactive analysis, then MapReduce within Hadoop will not be the best option. So like we talked in the first lecture, in the introductory lecture, is that when we're talking big data, so we're thinking, okay, I need capacity to store the data, so lots of hard drive. I need processing power to process the data, so lots of CPUs. And I need lots of memory in order to hold this intermediate, like in holding the data, processing the data on the go. So when we're talking Spark, this is key. So what Spark is going to do is capitalize on the memory part in order to speed things up. And we'll have a look at how it's going to do that. So the goals of Spark is keep more data in the memory in order to improve the performance. So that's why, like, okay, if the problem is with the input-output operations, so when I'm reading and writing successively to the disk, that's slowing me down. So the solution might be, okay, why don't I just keep it in the memory, and then I can conduct my operations there, and hence less I/O to disk, hence improve performance. And specifically when we're talking MapReduce, so we all see like MapReduce within Hadoop, it's like it's a bit tedious to program because you need to build every mapper and reducer yourself, and hence it can take a long time, specifically for complicated tasks. And I'm not talking complicated tasks like counting or joining. These are like still, they are trivial in terms of MapReduce. But if we're talking something like machine learning, when we're talking classification, then that's more like, that's very iterative and complex in nature of the computation. And hence, if you want to do that using MapReduce, it will take lots of time to do that. So any iterative operation, you need some sort of solution in order to make that more efficient. And for interactive data mining, if you want to have a look, if you're looking for something, if you're trying to query the data for quick insights, then you need some sort of interactive data mining, and hence like one of the goals of Spark. And from the programming perspective, so like we have seen that like Java library is for Hadoop MapReduce, it's like, okay, it's sufficient to do the job, but it requires lots of like lines of code in order to achieve something. So what Spark aimed to do is produce some rich API libraries in order to embed some of the like most commonly used methods or techniques in terms of, so that to minimize the programming effort for developers. So it would be more to be done with less lines of code. So in that sense, there are more built-in functions that can help you doing the job without the need for building everything yourself. So these are like the general goals for Spark, and we'll see how it will be trying to achieve these goals. So like the first thing when we're talking about, okay, keeping things in memory, so like for each, like the input of file, for the first, so like the input file definitely is gonna be on disk. Once it is read, and like now it's residing in memory, so Spark is going to try to keep it in memory for as long as possible in order, like, and we're talking here distributed memory, so the memory of all the nodes in the cluster, so not only in a single PC. And hence, like, when the results from the first iteration comes, it's going to stay in the memory, and then more calculations, second job is going to run, get that information from the memory, and then the second iteration, the output is also going to store in memory, and so forth. So in that sense, the intermediate output is not going to be written in the disk, it's going to be maintained in the memory. And for the, like when we're talking about querying the data sets, so it's going to load the file from, like the data from HDFS into the memory, and then the queries are going to be on the memory instance. So it's not going, you're not going to be querying the data on HDFS, but more like on the loaded data in the memory, and hence much faster. So it's like, it's approximately between 10 to 100 times faster on if you are relying on disk and like on network, like specifically because we're not only talking disks here, because if any of the data is in these different clusters and there is replication operation, then the replication is going to be on the level of reading and writing to disks, and hence also like there is heavy network utilization if there is replication. So that's like with Spark, it's trying to minimize this and hence achieve this 10 to 100 times faster operation. So like when you say, okay, what is Spark? So, okay, you've talked about it sounds cool. So I understand that it is something like it is providing me better, like faster solution than Hadoop MapReduce. It's covering the shortcoming of MapReduce, but what is it? Is it like, is it a specific tool? Is it something sitting on top of Hadoop? So like you can think about it is because Spark is the results of like advancement for Hadoop MapReduce. So don't think about it as they are part of each other, but more like they help, like MapReduce helped evolve Spark, because Spark is also using MapReduce, but in like a modification of MapReduce in order to be faster and process things in memory. So hence, like Spark is still utilizing the concepts of Hadoop MapReduce, but in its own special way that make it faster. So you can think about it as it's what's beyond MapReduce. It's an open source, so Spark, that's why it's Apache Spark. It's part of the open source tools from Apache. And it can help large-scale data processing. So it can help with generalized data flow. So it can help with calculating like faster calculation and analysis of data. And like for Spark specifically, it is written in Scala. And it has like APIs in Java, Python, R, and so forth. So, and there are still like, even currently Microsoft is doing some work in terms of integrating Spark into the .NET solutions that they have. So it was like 2009, it was developed by Berkeley. And in 2010, it became open source, and currently it's like like one of the top open source projects in Apache. So Spark, by nature, it is interoperable with Hadoop. So you can run Apache Spark separately, completely separate without Hadoop, and you can run it on top of Hadoop. Specifically, you can utilize HDFS and Yarn. So, but like they can interoperate together, or you can like run them as separate instances. There is no hard dependencies that forbid you from that. So it utilizes, as I mentioned, the in-memory processing. So, and hence it's make things much faster. And at that level also, it has the capability to process graph computation. So we'll have a look at what does that mean. So in terms of, okay, because there are like, when you think about Facebook, their whole data model is based on graphs. So when you're thinking about, okay, how they can like, and this is, I don't know, we're not talking a small graph, we're talking a huge graph, how they can process data from this huge graph, how can they query that graph on the fly. So graph processing is also an important aspect, and Spark help with providing the ability to do that as well. And like, since it is like to support popularity, it has their API for Scala, Java, R, Python. So, and for it has also its interactive shell. So you can like submit jobs manually using if you are using Scala or Python, you have the interactive shell that you can submit jobs directly. But Spark, when you look at it, it's not a modified version of Hadoop. So don't think about, okay, Hadoop next version is Spark. It's not that way. It's a standalone project. It has some advantages in terms of overcoming MapReduce shortcomings, but that doesn't mean that it's the best solution for all jobs. So even like when you're thinking, okay, then does that render Hadoop or Hadoop MapReduce obsolete? Definitely not. Because like as I mentioned now, it's like when we're talking about processing and keeping the data in memory, then we are past the commodity hardware. But like previously when we talked about Hadoop, we said that it utilizes commodity hardware. So you can have laptops with 4 gigabits of RAM, like 4 or 5 of them. Each one of them is a node, and you have your own cluster. Perfectly fine. But when we're talking about, okay, Spark, and it tries to keep the data in the memory, then you need a bit of mid to high-end nodes in order to be able to do that. So you cannot you efficiently run Spark cluster on commodity hardware, because then it will have some, if it will not provide you with, specifically if you are thinking stream processing and I will need interactive queries, then it will not achieve that job. It's going to be run. There is no problem. Even if it is a single node, we'll have a look at, there is a deployment mode, which is a single node Spark. That's perfectly fine for testing and for you guys when you're running your assignment too. So you don't need a big cluster. Your single node cluster is fine. So it's a standalone node. That's perfectly fine. But if we're talking production, then you cannot rely on commodity hardware, because then you will not get what you are aiming to with fast processing, I want to stream processing, and on-the-fly query, and so forth. And hence, here, when we're talking about, okay, clusters, that's more that job, then it would be more cost efficient to rely on Hadoop rather than to go to Spark and invest further in the clients, or in the nodes. And for the Spark is not dependent on Hadoop, so you can run it completely standalone. But if you want to make use of Hadoop distributed filing system, because as we talked before, HDFS provide you with this ability of high availability, high fault tolerance. So if you want to utilize that, you can run Spark on top of HDFS. And you can also, on the other hand, utilize Yarn as your job scheduler. Because as we'll see in a bit, that's Spark as a cluster computing technology. It also have resource management. So rather than relying on its own resource management, you can utilize Yarn to do that. So they are compatible in that sense. So Spark is, when you look at it, it was first developed in Berkeley. So a lot of Berkeley's data analytical stack rely on Spark. So what they have is the core part is Spark Core, what they call Spark Core. It's the core API. And then on top of that, they have different components. Spark SQL, which is the SQL query-like language on top of the data in Spark. Spark Streaming for real-time and stream processing. GraphX for graph computation, and MLib for machine learning. So for them, because Berkeley, when they built Spark, they had their own already available tools that they built on top of that. So, and still they are currently also available for you, and it's open source. So you can utilize these components to initiate these tasks and do machine learning and do graph computation and so forth. So when we're talking about how can we run Spark, so where does Spark run? So Spark can run using its standalone cluster mode, so perfectly by its own. There is no Hadoop, there is no HDFS. You run it on your PC and that's it, perfectly fine. You can run it on top of Hadoop Yarn. So in that sense, Hadoop is going to be doing the job scheduling and resource management for you. Or you can run it on top of Mesos. Mesos is a cluster management tool, also technology from Apache. So you can run it on top of Mesos in order to do also it will help you with the resource management and like the task allocation. It can also run on Kubernetes. Currently, like Google is investing lots of that in order to allow Spark to be deployed on Kubernetes. And there is also lots of Spark-based cloud solutions like Databricks, which is currently the active contributor for Spark on open source community. So there are already like also available cloud-based solutions that allow you to run Spark. So sorry. In terms of data sources, so this is like where Spark can run, but in terms of where does Spark read the data from, so it could be like your local file system. So if we're talking about the standalone cluster node, then it's going to read the data from your local file system, just like any file. It can read from Amazon S3. If you're building Spark on top of HDFS, then it's going to read from Hadoop distributed file system, all the data. It can also read the data from HBase or Cassandra, or like these Hadoop ecosystem components that handle more like different table-based or NoSQL technologies. So like Spark is very flexible in that term. It's allowed to consume data from different sources in different formats and allow you to do processing on this data. So as I mentioned, like Spark, like the developers of Spark, they tried to make things easier for like whoever using Spark. So it is not limited to the MapReduce model. So we see like within Hadoop MapReduce, there's like you have a specific model that you need to follow. You need to create mappers, you need to create reducers, and then like, so it's like, it's the case all the time. But when it comes to Spark, they try to make it more permissive. So they also provide rich library that allow you, that provide you with built-in functions that can make your life easier. And Spark by nature, it's already managing the memories. Like when we're talking about, okay, it's gonna keep the data in memory, it's gonna do this, it's gonna maintain all the data to make it more fast and read the data from memory and write the data to memory. Spark manage all this by itself, so you don't need to, as long as you specify like some things like how many partitions, like how the data, how many partitions you are creating. We'll look at that in RDD. But like in general, the management of memory is up to Spark. And at the same time, since Spark like acknowledge that, okay, I want to support like the interactive query of the data, so it also allow caching of data. So even if like there is this intermediate results, or like the end result, let's say, that was stored in memory, and then like, let's say for the second job, this result is like overwritten because there is another job is coming. But you can have the ability, if you know that, okay, I'm using this intermediate result for two different jobs, like I'm counting this and I'm sorting it at the same time. So you can cache that data, you can persist it in the cache in order to, rather than you reread from the disk, you can call it from memory and so forth. So there is more like capabilities to persist the data in the cache in memory if you know that your program require that I want to access this more than one time, and hence you minimize the time loss. And like for us, like when we're talking about Spark, it's also one of the any important aspects of cluster computing. It needs to maintain good fault tolerance. So definitely you don't want, if one of these nodes, because we're talking a cluster now, you don't want that one of these nodes, if it fails, then your whole job is rendered useless. Now you need some sort of fault tolerance. So in HDFS, we saw that there is replication. So if there is a node that's failed, there is another node that you can replicate the data from that node and then re-execute. With Spark, it manages this differently. So what it does, it's going to look at, okay, what this portion of data, the partition of data that that task failed, and it's going to re-execute the step before it. Let's say an example that you have 3 iterations. Let's look at. Yep. So let's say that for the results from the first iteration, like you get some data and stored in memory. And then in the second iteration, one of the partitions, one of these nodes, one of these slave nodes failed. So what it's going to do, it's not going to replicate the whole node. It's going to redo the iteration 1 for that specific partition of data. Because like here, we're talking about first iteration, second iteration. So I'm not going to go get the data from the source and redo everything. I'm just going to go one step back and try to redo the operation that happened on the data that's stored so that I get the same result. So I recover from that fault. So it is, in a sense, faster than reading from disk and redoing the operation, because in that sense, you're just going one step back and trying to recover from the fault that happened. Yeah, so that's what I said, with the re-execution of application. So it's just going to go one step back, re-execute the job, and get results and store it in the memory. And hence, it is faster than replicating the whole node and then redoing the job. Because like anything that's involved replication and disk operation, that means more time consumption. And hence, it's against the goals of Spark. Any questions so far? So it's important that you differentiate, okay, there is difference between Hadoop and MapReduce, Hadoop and Spark, but nevertheless, one do not put the other as obsolete, and at the same time, it's it's more tools in your tool set. So it's not going to be, I'm only doing Spark for the rest of my life, or I'm only using Hadoop for the rest of my life. It's always going to be more job oriented. So what's the type of the data that you have? If it is more one batch kind of job, and when you have a chunk of data, you throw it at your MapReduce computation, and then you get results or final report, then Hadoop MapReduce might be more cost effective. And there are things also we'll talk about later in terms of even not only cost efficiency, but even for security. Because when we're talking about Hadoop, it's currently, let's say it's more mature than Spark. So it has more security controls on top of the Hadoop ecosystem. While with Spark, it is less control. That's why most of the time they try to run Spark on top of HDFS or on top of Yarn in order to benefit from the security features of Hadoop. So these are things that sometimes make value rather than you invest on a customized solution. You can just rely on existing features for Hadoop, and hence they can balance each other. Okay. So when we're talking about Spark cluster, so in order to use Spark, developers need to write a driver program, it's your Spark application. and then it connects to the cluster worker. So you have like, just like with Hadoop, you have more like a main node, which is here the master node. And you have your master, like your driver application. And then you're submitting these tasks to the worker nodes, like your slave nodes, and providing them these portions of data. They do the processing and send back the results. So the notion is similar, but like here, the crucial bit is like the data is residing on RAM rather than it's residing on HDFS or a file system. So let's look at the Spark workflow. So like here, you're building your application. So this is your application, your driver program. There is something within Spark called Spark Context. So like this is like the main object that you can initiate Spark jobs using. And then through your Spark Context, you can define, okay, how many nodes in my cluster? Is it like defined, is it a local implementation? So it's a single node cluster. Or do I have many nodes? And hence then master, the cluster manager is going to manage these slave or worker nodes. And for each worker node, which is like let's say terminal here, whether it's a PC, whether it's a blade server, for each of them, we have what's called the executor. The executor is going to execute a single task for Spark. So on a single node, it can have multiple executors. So if it is running more than one task, that's possible. But like for that, it's definitely like depending on the memory utilization and the rule that you set in the cluster manager. Do you allow that? How many you allow, and so forth. And like for the data, you can take that data from, as we mentioned, HDFS, Amazon S3, local device, the cloud, or whatever. So in that sense, like here is like generally like similar to what we had in Hadoop. It's also like there is main nodes and there are slave nodes. And then the interaction between them, like you are going to run, configure that cluster manager, how many nodes it can accept for each, what we'll talk about the RDD in a second. For each RDD, how many partitions do I allow to submit? Which is the RDD is more like the data format for the Spark to process. So in that sense, you're going to say, okay, how big is the block of data? How big is the partition of data? How many workers do I have? So that like you manage this in order to be more efficient. And hence the rest is going to be similar to what's the workflow for Hadoop, that when the worker node finishes its work, it's going to send the results back in the cluster manager, and then it's going to send the results back to the driver, and hence you have your output file that you can display or store on disk and so forth. Any questions about Spark workflow? So for worker nodes, so we said like the worker nodes is your typical end node, whether it's a PC, whether it's a blade server, whether it's a server or whatever. So like they are machines that run executors. So these executors, as I mentioned, like they take tasks that they want to execute by the cluster manager, and hence they do the job, and then they get the results for the driver. So for that, like for one worker node, it can have one JVM per worker node. So you cannot have more than one JVM on the worker node, and hence like you can spawn more than one executor, But like within the worker, like you have one JVM that you can have multiple executors. So you can have multiple tasks running on the same machine at a single point of time. For the executors that run the task, so when we're talking executor, it can run one task. That's why the worker node can have multiple executors, because if it wanted to run more than one task, it needs a certain task for each, a certain executor for each task. Each executor cannot handle more than one task. So one process, one executor. And like in that sense, depending on like internally what's on your machine, if they have multi-threading, if there's a thread pool, how you're utilizing that in order to be more efficient. So this is more like the introduction for Spark. So like generally what's Spark, how it works internally, and so forth. We'll have a look now at some of the internals of Spark that make Spark work as is now. So there are things like, this is like the most important part, the RDD, which is the data format the data object that Spark handles in memory. So this is the persistent data object in memory, and hence it allows all the fancy, nice things that we talked about before. So let's have a 5-minute break, and then we'll continue with RDD. Just a second. Okay.
So it's mostly the data type. So I'm not really sure about the writable data type. Can you explain like why do we need writable, like for input and output?
Okay. Yeah. So the writables as a writable is responsible for serializing and deserializing data.
Yeah.
This is important because we like in a normal setup we have a cluster.
Yeah.
So the data, when it's passed from one node to another, you need some sort of bits serialization to pass the data from one node to another. So this is Hadoop specific, that you need writables. It cannot take integers or like floats or strings. So this is like they have their own wrappers, which is the writables. So in order to serialize and deserialize the data. For the case of like normally you can rely on the normal writables, like the int writable text or this, but for some cases, just like the assignment, you need some additional writable. So because like the ones that's available int long text does not match what you have now. So you need something to custom, more like a custom writable.
So essentially the image mapper and reducer, like the input. So text is also just like a writable for string, right?
Yes.
Okay. So you need writable for all like key value.
Exactly.
But like, is it possible? Because I think I was doing, and then like, can I also like all use tags just before the last time?
Yes, this is more like the inefficient way of doing it. Yeah, because like you can't say, oh, everything is text.
Yeah.
It's gonna work, but absolutely inefficiently.
Okay.
Why? Because you're gonna consume more memory that you are supposed to consume in the first place. That's why we need custom writables.
Yeah, I also have like, I can't think of like the memory thing clear. So I have also like another one. It's like I have like different writable for each like input output key value. Because for some of they have like composite like value things, right? And then for that I kind of like create one for that and then like another one for like another output. Or is there like reusable write bold?
No, you just need to create, like for the first one, the first iteration, it is text.
Okay.
But the second iteration, you create your custom writable. So there is nothing, like if you use text, you are gonna be penalized, I think 4 points. For the second iteration. This is the first one, because the first iteration, it is text, you're reading a file.
Yeah.
But like the second iteration, you need to create your custom writable. Like we have the marking scheme saying that you need to.
So that means like you have to. Okay.
Yes, or if you want to sacrifice it, it's up to you.
Can you also explain about the comparable, like that?
Okay, yeah. So like the custom writables is helping you with serializing the data, the values. If you want to compare your custom writable, then you need to tell MapReduce that these keys are subject to comparison. Because by default, int writable, long text, they have like the keys are comparable. They have row comparable. But if you're creating your own, then you need to tell it, hey, these keys are also subject to be compared. And hence you need to do writable comparable.
So is it like only for the case that when the key is customized?
Yes, because like the built-in writables already are comparable, so you don't need to do anything about them.
So if the value is customized, we don't care about comparable, right? Like the value.
The comparable part is for the key, not for the value. Because you're not comparing, like let's say for the shuffling and sorting, you're not comparing values, you're comparing the keys, shuffling with the shuffling.
So actually like a data type is, I have a customized data type and then I create another one which the attributes is that customized writable. Is that like kind of thing that you can do, or would that be any?
Sorry, I can't understand what.
So it's like I have for example, like movie rating writable, so that it have like the attributes movie rating. And then I have like another writable which is like movie rating pairs. So it have two attributes which is like two movie rating writables. Is that like something like a good practice, or does that complicate the process?
So it's up to you how you, as long as you're treating it as key value pairs, it's up to you how you implement it.
It's okay.
Yeah, we don't have restriction in that regard, but that's like the only restriction is that you need a custom writable because you need to create a new writable for this case, the intermediate result.
And I think another thing that I was thinking I want to use tags is that I feel like it's like referring every time and also like creating.
Yeah, it's possible. Like as I mentioned, like possible you say, okay, I'm not gonna use MapReduce. I'm just gonna, because the data set is small, so you can just say, I'm gonna use Python and pandas and to do the job. So it's possible. Like everything is possible. But if you're thinking about this is data set like have billions of records, then if you rely on text, then the job will not run in the first place. So you'll just have like clogged jobs, and that's why.
When I was thinking is that because like if you're passing for like iterable, right? So if you're just passing like the data type is text, so does that like only use because you have to create like new object which occupies new memory?
Yeah, that's exactly the thing. So keep for each one you're creating a new object, and then
So
that's why
like,
it's.
if I use like customized writable, I have to like create so many like new,
No. Like because MapReduce already processed that, so it's not gonna keep it in memory. So it's like this is a new writable, so it's gonna deal with it just like the normal writables. So it's not gonna be memory consuming. No worries. Okay. Sorry.
Similar things. Because we saw this on forum saying that we have to use every writables. We have our own customer writable, which is storing the users and the scoring. Because the final output is movie pairs and then users and two scorings. we create our own custom writable to store one set of this data, and then store sets of custom writable in like for an array or something, and we output it. So what we're curious about the marking schemas. If this is true.
No, this is not part of the marking schema. This is more like a suggestion.
So suggesting we use.
So the marking schema is specifically say you need to use custom writables. As long as you're using that, you're fulfilling that. Whether you use array writables or not, it's up to you. If you find a better way to do it, it's like at the end. It's more like it's a project. It's your own project.
Yes.
So it's not gonna be everyone. No. This is not marking schema. Okay. This is more like he's providing maybe you can use this something.
Right. And hearing you guys talking about the key as the text and also the key as the customer writable. You're saying the as is writables it's more efficient.
Yep. So that's why we create. That's why we create the custom writable, because it's more memory efficient than using text. If you like create the text and handle the output as text as well, like the intermediate output as text, the iterable object is going to create a new object for each iteration and hence consuming lots of memory. So when you define your custom writable, it's not going to do that, and hence it's more memory efficient. So it can work if you use text and you don't create your custom writable, but very low efficiency, because if let's say you have 1 billion of records, it's not going to work. And at the same time, we specifically say use custom writable. So if you want the mark, you need to use custom writable.
Yeah, and that's strictly on the whole project, not just to the keys or to the value sets. As long as you use custom writable involved in this project, then it's not going to be scope reduction.
Sorry, what? So where would you use custom writable else?
I use it in the value pair, value key, value sets. But you can also use it in the key pairs, which are the final outputs of the.
So like movie pairs, you use it as a custom writable.
Okay, so.
Also, but we strictly refer to the.
Yeah, sure, no problem. So as long as you respect using custom writables, that should not be, you'll not be penalized.
Okay.
Yep.
I remember that you said on the lecture one executor can only process one task, right?
Executor, one task, yeah.
So why is there such kind of execute one or more tasks using that?
Yeah, so this depends on your technology. So if there is more let's say your machine is multi-threading, so it's actually what it has, it's more like it's virtual threads, virtual computers inside. So it will look at the multi-threading, it looks like at the thread pools, and say, okay, it will treat that as a new worker, a new executor. So it's just like a new executor taking a new task.
So it's it can only execute one task at a time, but I can.
Yeah, definitely. This is it can get another task on another time, definitely. So it's not gonna be gone after one task, but at a single point of time, it can only do one. So you can one worker can have multiple executors, but that depends also definitely that depends on the cluster manager, because you need to define okay, for each worker how many executors it can have, because if it is that your machines are 8 gigabits of RAM, so it's unlogical that you put too many executors on a single machine, because then the data cannot reside in the memory. So this is more management of how the cluster work, but there is no restriction in terms of how many executors on a single worker. Anyways. Okay, we're going to continue the lecture now. Enter RDD. So like with the existing systems, excuse me, we're going to start the lecture. So if you can be quiet, please. So in the existing systems, like a lot of like existing in-memory storage systems have interfaces, like depending on specific fine-grained details or updates. Like if we're talking about tables, then we say, okay, when we read and write these cells, then we can keep them in memory, then commit them to the table on our database. So in that sense, like there is more interfaces on specific tasks, like when you're talking about your normal relational database, that when you're doing something, you're actually committing on the memory, then you're actually doing that in memory and then committing on the writing on the disk. So like when we're talking small data sets or like small data, like smaller volume of data, that's fine. But when we're talking large, someone like on the go, that's not very efficient. So, and now also we're talking more distributed computing. So you have multiple nodes. And like, let's assume that, okay, for each of these nodes, the memory, like the data in memory also need to support fault tolerance. So there need to be some sort of replication of data in the memory. And hence, it can be very expensive if you're going to pass data from like one node to another, like from network perspective and so forth. So, and like even if you rely on like part of the memory, I store it on disk and then pass it to the network also, like it can create slower solution. So like the current solutions, it's either okay, it's catered for smaller data, smaller volume of data, or when we're talking cluster computing and replication, it's not gonna scale properly. And hence, there need to be some sort of solution that that support cluster computing. So it's more like memory storage and supporting cluster computation. And at the same time, maintaining some fault tolerance. So I need some efficiency and fault tolerance. I need to maintain that this is the data in memory. It's like I can maintain that data within parallel computing, and I can maintain some level of fault tolerance. If something happens, I will not lose my data and it will not cause me any issues. So to answer this, the resilient distributed data sets was created. So the resilient distributed data sets is a collection of objects that you can cache or store in memory across your cluster. So that's like satisfy the first thing, that okay, it's a collection of objects I can store or cache in my memory across the cluster. And hence, okay, that sounds good. And like I can manipulate that, definitely. Like if it is on sort of, if it is on sort of, I'm doing some processing, I need to be able to access that data, whatever it is, so I can have some parallel operators. And if there is some failure, so in the case of any failure, I need to automatically, let's say, recover from that failure, and hence the data is recomputed according to something. So RDD help you with this. So it allowed this memory to be distributed, stored in the memory of, cached in the memory of the cluster nodes. And then I can do processing on them, and I can recover in terms of there is any issue, if there is any failure, using what's called lineage. And you say, oh, we'll talk about what does that mean. Like this is what I talked about in a bit ago, which is recomputing the last step in order to reproduce the data. So this is what's meant by lineage in terms of fault tolerance. So like in that sense, it can allow me to do my usual jobs in terms of map produce jobs, or if I want to query my data, I can query my data using an SQL-like language. And hence, I can also perform iterative jobs. So now, like with RDD, I know that, okay, it provides me some sort of way to store my data in the memory. It allows more cluster distribution. It allows the operation to happen, and there is fault tolerance. So it's like, okay, this is more like, this is the ideal solution. That's what can be utilized in order to achieve what Spark is, what the goals of Spark are. So what's this RDD and how does it work? So RDD is a fault tolerance abstraction for in-memory cluster computation. So this is what's the definition by the people who invented the term and like who created RDD in their paper. You can have a look at the paper. It's like very informative. They explain where they specifically talk about Spark and how RDD helped into making Spark achieve its goals. And hence, like they are talking about all the features in terms of memory, cached memory persistence, and lineage in terms of reproducing the data, like the stages of data in terms of fault tolerance. So let's look at what RDD means. Resilient, the R stands for resilient. So it is, by definition, fault tolerance. So I can get any missing data. I can compute the last step to acquire the missing data or any damaged partitions in order to get the, like if I get a node failure, I can reproduce the data that was supposed to be processed by this node. So I can just step back, reproduce the data, and voila, I got it back. Distributed, so RD, the first D is distributed. So it can reside on multiple nodes on a cluster. So it operates like, it tries to operate on all the nodes within the cluster, making them share their memory. And hence it allows you to to execute Spark jobs on these nodes on the cluster. And the second D is dataset. So just to signify that it's a collection of partition data. So it's more like, it's okay, it's more what are these collection of objects of that I'm trying to store and hence process and get the information from. So RDD is the core data abstraction in Spark. Like what we have talked about in terms of Spark being processing data on memory, doing streamline processing, doing interactive query. It's all like due to RDD, because of RDD. That's why it's very important how the Spark jobs are being executed. So the qualities of RDD is like, first, it's in memory. So it is a collection of objects not persisting on the disk. It is persisting on the memory. So it's stored in memory as much as possible. So it's going to look at what's the capacity of that node, how can what's the maximum size that I can occupy, and what's the maximum time that I can reside there. So it's trying to persist in the memory as, in terms of size as much, in terms of time as much. This is like definitely depending on your policy also. So you need to define, okay, what's the reasonable, like if it is an intermediate job that I do not care about, then I can scratch it early. But if it is a possible that an intermediate job giving me an output that I can utilize for more than one job, so I'm calling that data more than once, then you need to make it persist further. By nature, RDD is immutable, so it is only read-only. So once the RDD object is created, you cannot modify it. So it can be transformed. So one RDD can become another RDD, but the existing one still reside there until you drop it. You cannot change the RDD object itself. So you need to keep that in mind in terms of operations allowed on RDD, is that it is immutable. So you cannot modify it. You can transform it only to a new RDD. By nature, it is also lazy evaluated. What does that mean? That means like when, let's say like you have a blob of key value pairs and you did some mapping or something. So you applied some transformation function on these key value pairs. By nature, when you're writing your program and you're saying that it's like it needs to be the first thing that I need to map this to that, I need to the second step doing this. So within your program, even you are indicating the flow of the logic, what is going to be done. Spark do not initiate, do not start that job until there is what's called action. So the action is more like the final reduce function. That's aggregate all the results. So by nature, each of the RDD is not transformed, is not processed until there is an action. So it's not like going to be interpreted once by once and then there is a middle stage before there is a final stage. There need to be an action saying like count the number of keys as an example, and hence after this it will start from the flow of the all these like the RDD transformations one by one, executing them. So that's why like here it's provide better memory efficiency, is that these RDDs are not transformed unless there is an action to invoke this transformation. There is a trigger for the execution. These RDD are cacheable, so you can specifically say that, okay, I want to persist this RDD in memory for this time or for this number of job iterations and so forth. So hence it can allow you more efficiency if you know that you're gonna call this RDD more than once, and hence it can, like rather than it is regenerated or written in memory, it can make things faster. By default, it is to reside in memory, but you can specify like, okay, I want it to be persisted, so as much as possible it stay in the memory. Parallel, because like definitely when we're talking cluster, so it need to be, there is a possibility to partition this RDD so that it can be processed in parallel, so that like it's not gonna be one chunk, like one big chunk of data that you need to handle or a single machine. So there need to be some level of partitioning so that you can distribute it into more than one node and hence allow processing data in parallel. It is typed, so just like what we saw with like for Hadoop, definitely for RDD it's also typed, so there is integer RDD, string RDD, so it also, you need to highlight this when you're developing your application of, okay, what am I trying to consume from the data? What is the type of the data? And partitioned, so as I mentioned, like for the sake of parallel processing, the RDD you need to be able to partition this RDD into smaller partitions so that you can distribute them to the nodes, and hence the executors can perform the task on this partition and then get the results. So you need, it's by nature, there is the ability to partition the RDD in order to distribute these partitions to the cluster. Any questions about RDD traits? So when it comes to RDD operations, so there are two operations for an RDD. So there is what we call transformation. As I mentioned, like RDDs, you cannot modify an RDD. It's immutable. So once you create, it's created, it cannot change, but it can transform. So you can apply some transformation function and transform this RDD to a new RDD. So as an example, like group by key as an example. So this is a transformation function, and you just want to say, okay, I have these key value pairs, I want to group them by key. So this is going to create a new RDD for a group by key. Then the new RDD is going to be grouped by keys and so forth. So there is a new RDD that's the result from the transformation applied for the first RDD. So here it is like transformation function. When it is an action function, so the action is more like, okay, I don't want to, not necessarily I'm going to create a new RDD. So maybe I'm creating a final result, which is like a text file or display or something. So in that sense, I'm executing an action, like an end action over the RDD to generate results. So in that sense, it can be like just what we, for the reduce, the final aggregate reduce function. So I'm saying that, okay, these now are my keys, so do reduce and then give me the final results here and store it on file, save as text file or something. So this is an action that you can perform on an RDD to get final results or to get results. So in essence, like what we talked about in a bit ago when I said RDD are lazy by nature. So when a transformation function is applied to an RDD within your code, it's not going to execute unless like the action is invoked, so the action is executed. Then it's going to go back to the transformations, and one by one it's going to execute them. So that's like, it's not going to transform RDDs and store them in memory, and then I don't know what's going to do with them. No, it's going to be more like, okay, unless there is an action, so there is, I know that there is a save as text file or count or collect, and then I go back, okay, what is this collecting? Was the previous transformation, and then go back. It's more like a graph. I transcend from one point to another, and then start the transformation from top till I reach the action, the end action, and produce the results. This is more memory efficient because you don't want to keep transformation in the memory and you don't know for how long. And hence, always like the lazy scheme is better in that sense. So for the RDD, like how you can create an RDD. So by nature, like it depends on the creating an RDD from a data source. So whether it is like, okay, I have this collection of data, lists or arrays, and I want to parallelize them. So I just go and apply some functions in order to make this list or array parallel, or like, sorry, an RDD. I can get an RDD by applying a transformation function on another RDD. So you have an RDD already, an RDD object, and I apply a transformation function like group by key, and then I still get another RDD. Or it can be a file used in, stored in HDFS and or any other storage system. So I'm reading the file and I'm converting that to an RDD and starting to manipulate that in my Spark job. So like possible transformation can be map, filter, possible actions, count, collect. So this is like a normal flow. Like here, if let's say we are trying to parallelize the list. So when I apply an RDD function to a list, I can get this new RDD created. I can apply this transformation function, filter. I get a filtered RDD. I can apply another transformation function, map, and I can get map RDD. And then I apply an action function here, which is collect, which is an action, where I will get the final results. So these are like the flow of how you can work with an RDD. So you can create an RDD, transform it, and then apply an action over it to get final results. So that's like generally how we work with an RDD. But like, let's say, okay, in terms of creating an RDD, like, okay, so if I want to create an RDD from file, if I want to say, okay, I have this file that it's a text file, and I want to create an RDD from that file, and I want to partition this RDD for 4 partitions. And so I consider for that text file, each element is a line of text or like line of the input. So here, like when we're using Java, I say Java RDD string, because here we're dealing with string. Destination file, which is my RDD now, is the text file reading to data.text, and I specify that I want it to split into 4 partitions. So here, like if you don't specify the number of partition, what it's going to do most likely is going to the cluster manager is going to look at how many nodes you have in your cluster, and then put the number of nodes in that term. So if you have 5 nodes, it's going to say number of partitions 5, and so forth. But if you there is a specific use case that you say, no, I know that I have 2 nodes, but I want for each node have 2 partitions, and hence 2 executors for my purpose, and then you can specify the partitions for. So if you don't specify, it's not gonna crash, it's just gonna rely on the number of nodes. If it is a single node, it's a single cluster, and that's it. A single partition, and that's it. So, and if I want to turn a collection into an RDD, so here, like internally, like I have an array or a list, and I want to convert it to an RDD. So I can just say, okay, Java RDD, this data, destination data, parallelize, and I pass the list object. So it's gonna just take that and turn it into an RDD. So like as you can see, like it's not very complicated, but in terms of you definitely need to, because Spark, in order to be able to perform all these awesome goals that we mentioned, all your data that it's gonna handle need to be an RDD. So for Spark transformations, so the transformation functions, it's just going to create a new data set, a new RDD from an existing one. So the transformation is, like you can think about it on the level of map. So map can provide you with like an intermediary key value pairs, but it's not gonna produce an end value or end result. So it's gonna just transform your data from one data set to another, transform an RDD from one RDD to a new RDD. By nature, transformation is lazy use lazy evaluation, so they are not executed until there is an action invoked, and hence, like Spark, keep in mind, records the, like in a graph, that's what's the process that's like these transformations are going to occur, and hence until the action is executed, then it starts doing the transformation. It doesn't do the transformation and keep them in memory, and like this is because not efficient and then memory consuming. Spark optimizes the required calculation according to this graph. So it depends on like, okay, how many transformation I have, and then according if you have a memory caching policy, you say, okay, this intermediate result, I want to cache it for like 3 hours, or I want to cache it for multiple 3 iterations and so forth. So depending on this, your Spark can optimize the required calculation to provide you make use of this persisting rules or the policy that you have set, and at the same time it's going to recover from any failures. So if any of those nodes, they're doing the transformation task, if any of these nodes have failed, then it's going to redo the transformation function in the step before in order to generate the new transformed portion of data. So you can have some of the look at some of the transformation in the documentation, in Spark documentation, like map, filter, flat map, all these like. And as you, if I encourage you to have a look at them, because it will show you that actually the Spark library is very rich in that regard. So there is already lots of built-in functions that we'll have a look at the word count example in a bit. But you feel like, okay, this is much easier if I build it than if I build it from using MapReduce, because that's the one of the advantages of Spark, is that the library is rich. So there are already built-in functions that can help you execute the job without recoding the whole logic. For Spark actions, so it is like more like it's the trigger that initiate the recipe of transformation. Sorry. Let me just take a sip. So let's assume this way, like as this example. Like if you have, like you are trying to cook dinner for today. So in essence, there are like more steps for like your food, like you got some eggs, and then you're transforming this egg from one state to another. So by nature, so whatever, like when you're starting cracking the egg, you cannot roll back to the previous states. Like you cannot put the egg back and back to the fridge. So like Spark also rely on similar way of executing like the events. So what is going to look at the transformations that you have already set up. And once there is the trigger, the action trigger, let's say collect or count, once that's executed or like it's triggered, that action, then it will start from the flow of transformation from the first step, which is like cracking my egg, scrambling the egg, blah, blah, blah. So that's the thing, is like it's going to be more like a one-way graph, that's more directed graph of transformation from one state to another, and hence you get the final result, which is the result that you want from the computation. So this is like the action is, you can think about it as the trigger that initiate this flow of directed graph to execute the computation. So here, if let's say you want to count, like word count, and you're saying like count these words in this file, and then so once you initiate this action, then the transformation of first mapping the keywords to one, then aggregating the ones and so forth, like what you did with the word count. So it will initiate this transformation one by one till it gets the final results and store it as a text file. So this is like Spark way of doing things so that it does not waste memory. It's only wait for the trigger and then start execution, and hence keep the memory free for other tasks. Because like by definition, Spark is not like you're gonna run only one Spark job. Probably you're gonna run more than one job, and hence you don't want to waste your memory. Have a look as well at the documentation and some of the some actions function on RDDs, and like also it's very rich in that regard. So you'll find that it makes your life much easier as a developer. So let's look at an example that we talked about in Hadoop MapReduce, which is the word count. But now we look at it from Spark perspective. So like from the look at it and you say, oh my God, we wasted too much time. So like this is everything you need to run word count on Spark. So there is no mappers, no reducers. So that's why it's like, that's why I said it's very rich in terms of the library. So here, like you're defining your pair, you're consuming like the RDD, the original RDD from file. So you're getting the text file, let's say from HDFS. And then you're creating pair RDD. So you're creating a new RDD by applying a transformation function. So you're counting here in this regard. So you're counting, you're doing flat map on that. So you're mapping all the key. In that regard, it's still a text file. So you're creating the key value pairs, depending on splitting by a single space, and iterating through all the words in this single text file, and then map to pair, and you're like creating for each of these words, you're creating a word plus a single default value, which is 1. So it will be dog 1, cat 1, car 1, and so forth. So you're iterating through the whole text file and creating this pair of word plus hard-coded value, which is 1. And then you're saying reduce by key. So I'm telling you just do a reduce by key, and voila, I just need to save the count of how many keys, the key value pairs I have, and I count all of them and store them in the file. So in that sense, like within these few instructions, I can execute the word count example that we illustrated last time without like creating a mapper, creating a reducer, and then like doing all this. Like this is all within the Spark library. It provides you these functions that can make your life much easier. And hence, like this is definitely make your life easier on bigger, more complex programs. So like you can think about it, that's the important part is that, okay, if it is simplify things, then if we're talking about, let's say, a machine learning classification algorithm, then definitely, especially with more iterative jobs, then it makes my life much easier as a developer, because I don't need to create many mappers and many reducers, and then just cascade all of them, and then just get these intermediary results and feed one from one to another and so forth. So like Spark, simplify things, make it more efficient for faster, and make it more efficient for developers because like it's more, the library is rich that allow you to do many things in less lines of code. Any question? Okay, so we talked about the fault tolerance. So one of the important aspects of Spark is the fault tolerance bit, and that is achieved through the lineage graph. So what it's going to do is, like, RDD is, as I mentioned, lazy in nature. It's not gonna, like, every transformation you mention in your program, it will execute right away. No, it's gonna just like, okay, I noted down that you want this one to be mapped, you want filtering, yeah. I'm storing all this in a directed graph, but I'm not executing anything until you trigger the action with like collect or count or something. And hence I start executing like the transformation functions. So how does like Spark keep record of that? Is through the lineage graph. So it's actually a directed graph that it's going to note what are the transformations recorded for this RDD. And okay, like one by one, as I mentioned in the dinner egg example. So it is a one-way graph. So like once you crack the egg, you cannot roll back. Once you scramble the egg, you cannot roll back, and so forth. So from execution perspective. So we know by nature that it is a directed graph going one way only, and hence I can say, okay, if something happened, if one of the eggs fell on the ground, I can just repeat the previous step, so I get a new egg and I crack it and apply the transformation, which is cracking in this sense. So if something went wrong and I want to recover from the fault, I just need to step back from this graph. We mentioned that there is a graph of steps of transformations. I just step back and then redo the execution on that, like redo the calculation or the transformation, on that portion of data. So I know that node number 38 is down and it had the portion of data this. I just need to go back to one step back, which is like for where did the node 38 got the data from, and then I redo the transformation on that same portion in order to get the data. So I'm not gonna replicate the result. I'm not gonna replicate the whole node in order to recover. I'm just going to step back and redo the transformation. And that's with the help of the lineage graph. So let's say here for an example. So if, let's say, I'm processing log files, and for each within the file, a huge text file, each line is a log record. So here I have RDD1 is lines, and then I apply filter, and I want to find errors in this log file, so I'm only interested in errors. So I apply filter, and then I'm only interested in HDFS errors, so I apply another transformation function, which is another filter with HDFS. So I'm saying, okay, HDFS errors only. And then the end result, I want to, so in that sense, also transformation in terms of, I want to map according to specific time. So I want to do mapping according to time field. So that's another transformation. So if by any chance that one of the nodes had an issue with like a portion of the data, a portion of the RDD for the HDFS errors. So I just need to step one back to where it was RDD2, since like RDD2 is what we mentioned, it is immutable. So it's not gonna be changed. So I know that the data is correct in RDD2. I just apply filter contains HDFS on that portion, and voila, I replicated the result from the last transformation. So within the error fault tolerance in Spark, there is no need to replicate the whole node, just step back, and that's like all this information. The lineage graph is recorded in Spark. So Spark already knows that it's like these are successive transformations. So if something went wrong, just roll back one step for that portion. So this is you're not gonna do yourself. So Spark manages this by itself, but like this is how it does it. Just like in terms of, okay, is there some sort of magic? No, there is no magic. It just rely on this directed graph. It knows that this is the sequence of transformations, and if something went wrong, I just need to step back and do this, and hence get the results. Any question about lineage graphs? Okay, so we talked in the beginning about the driver and Spark context. So Spark context is like, it's the entry point to Spark. If you do not create your Spark context object, you cannot start your Spark jobs. Because like this is like more like it will invoke the configuration file, reading any policies, what you have set, how many nodes, how many partitions in each, executor, in each node and so forth. So all these data is invoked when you initiate your Spark context. Once you do that, you can start with like creating RDDs, create accumulators, broadcast variables. So like all the Spark jobs, unless you initiate a Spark context, you will not be able to do that. So what does that mean? From developer's perspective is that when you're developing, you need to invoke the Spark context class in that sense, and then start your development. If you are using a native client, like an active client, interactive client, it's by default, like let's say if you're using a Spark interactive client, by default, the context is already created for you. So if you're in a client, then the context is already created. You can submit jobs if you want. But if you're developing, then you need to create the context yourself in order to go on with the like your development and submitting your Spark jobs. So Spark context is important because it tells Spark what it needs to do, what's in the cluster, how you should manage it, and so forth. Okay, so in terms of RDD persist, okay, how many slides do we have? Okay, not too much. Okay, so this is relevant to the Spark context. So I'd rather spend 1 minute on this and then we continue with the rest. So there is currently, like, you might come across what's called Spark sessions. So I haven't included here because it complicates things a bit. But nevertheless, for you who's interested in this, feel free to Google it. So what Spark sessions is, like, okay, now context, if you are creating context invoking Spark jobs in, like, normally when you're using the client or your